So we turn to the foundation that brought us to an understanding of the scientific concept of energy. And this began with one of the most famous stories in science, and that involved Sir Isaac Newton. And Newton had moved from Cambridge home because the plague had struck Europe and England. And so Cambridge University asked all of its inhabitants to move home so that they wouldn't pass the disease from one to another. So Newton was sitting out in his backyard observing his apple orchard. And this story sounds a little far-fetched, but there's actually a great deal of truth to it. So we're going to follow it because it turns out it reveals to us a great deal about how we came to understand the conservation of energy. And the first thing Newton did was that he watched his backyard and he noticed that an apple would drop off the tree. And when it dropped off the tree, it would accelerate to the ground. And he realized that if he isolated the trajectory of that apple and ignored what happened when it hit the ground, he actually was seeing something extremely important. And he noticed and articulated the fact that force is an agent of change. Then he recognized that mass remains at rest or in uniform motion unless acted on by a force. And we take this for granted today, but this was revolutionary. This is Newton's first law. Next, he said that force results in an acceleration. But moreover, that acceleration is proportional to the force applied to that body. The proportionality between acceleration and force, that turned out to be extremely important. In fact, this proportionality between force and acceleration was the foundation for Newton's second law of motion, that the acceleration of a body is proportional to the force applied to that body. But what is the proportionality factor between force and acceleration? That was the question. And Newton hypothesized that that proportionality factor is the mass of the body. That is, that we would write that the force was equal to the mass times the acceleration. So the proportionality between force and acceleration is converted into an equality by recognizing that the mass is in fact that factor. And he came to demonstrate that this is a correct hypothesis because if he took a large mass, m, which we'll designate with a capital M, and he analyzed, again, by watching these apples of various sizes, as the story goes, fall from the tree, the acceleration of a large apple of mass capital M is equal to the force on that large apple divided by the mass of that apple. If it was a small apple, the acceleration was equal to the force on that small apple divided by the mass. But he noticed that those two apples would hit the ground at exactly the same time, and that meant he could equate those two accelerations and deduce the fact that indeed that proportionality was the mass involved, and so the force is equal to the product of the mass times the acceleration. So Newton's key insight was the following. He asked the question, which was a fairly simple question, if I have this apple sitting on the ground, what does it take to restore that to the position it was in before it dropped? And the answer to that is that if I elevate it up from the ground to its original position over some height h, the key thing is I've done work on the mass. So we know that work is equal to a force times a distance. A greater force over the same distance results in more work done, and the same force over a larger distance results in a greater amount of work. And we could tell this because if you push a block of stone along the ground, the total amount of work you have to do involves both the force that you have to apply and the distance over which you execute that force. Well, we know how to write the force now. That's the mass times the acceleration. And so we need to multiply that by the displacement. But the acceleration is the acceleration of gravity. That's m times g. And in our case, we want to elevate this a distance h. So we multiply the mass times the acceleration of gravity times the distance over which we've done work to restore that apple to its position. But it turns out that work is the same thing as energy. And Newton realized this, and he called that energy potential energy, and we'll designate that as PD, and that potential energy is energy of position, and that's equal to mgh, which is the work required to place it in that position within a gravitational field. Well, this is a big step forward, because what was also recognized by Newton was that all that was happening when the apple dropped off the tree was that the energy of position, the potential energy, was being converted to kinetic energy. It was accelerating downward in the gravitational field. So that meant that we could immediately write an expression for the energy that's equal to the potential energy plus the kinetic energy. But we have the expression for potential energy, that's mgh, and the kinetic energy of the moving mass was 1/2 mv squared. And it's interesting to point out that it was already recognized that kinetic energy of a body in motion was the product of its mass times the square of its velocity. So the kinetic energy part was simple. But what Newton pointed out was the change in this total energy, E sub t, was equal to 0. And that meant that I can write the change in energy, total energy, as the final energy minus the initial energy. Now I can examine what actually happens when, for example, I fire a projectile from the ground, and let's define the height as 0 at the ground, and as that body moves vertically, and I can move in time to keep these separated, as the ball rises, the kinetic energy that was initially given to it, the 1/2 mv squared, is seamlessly being converted to potential energy until we reach the top of the trajectory, and at this point the kinetic energy is 0. But it has a potential energy equal quantitatively to the initial kinetic energy, and so as it descends back down in that gravitational field, that potential energy is converted to kinetic energy until it reaches the ground again. And so I can represent this as a bar chart. I start with all kinetic energy. As it moves vertically, I convert that kinetic energy to potential energy until I have all of the energy in potential energy, and then as the mass begins to descend, it's trading off seamlessly and accurately the potential energy for kinetic energy until it hits the ground again, and that final kinetic energy is exactly equal to the initial kinetic energy. And of course we're assuming here that there's no friction, and in most of these cases, in mass moving in air, the friction over small distances is very small, but to be absolutely precise, we have to be careful that we have no friction involved if that final kinetic energy is equal to the initial kinetic energy. All right, so our total energy then is equal to mgh plus 1/2 mv squared, but our change in energy, change in the total energy, which is the final energy minus the initial energy, is now an expression that we can put specific quantities into, because my final energy is equal to 1/2 mv squared final plus mgh final minus exactly the same quantity, but for initial conditions, 1/2 mv initial squared plus mgh initial, and that is identically equal to 0 by the conservation of energy. Well, that means I can equate those two. I can write 1/2 mv final squared plus mgh final is identically equal to 1/2 mv initial squared plus mgh initial. Well, if I adopt my previous configuration and I start at the ground where the potential energy is 0, then my initial height is 0. When I reach the top of the trajectory, my final velocity is 0, so I can set that equal to 0. And I can find the relationship between the height that that body reaches and the initial kinetic energy by simply equating what's left in my equation. mgh final is equal to 1/2 mv initial squared. So if I want to reach some height h, I simply solve for the required initial velocity, and that initial velocity is equal then to the square root of 2 times the acceleration of gravity times the final height that I wish to reach. And the reason it simplifies is that the mass cancels out of both sides, and I have my expression for the required initial velocity to reach some height h. So just to review, we did the conservation of the combination of potential and kinetic energy following from an initial state to the height h, and we can calculate the required initial velocity to reach some height final.